Hello again, Physics 20s. In today's lesson, we are going to talk about two important fundamental wave properties. And by fundamental, I mean that they are characteristics that only a wave could exhibit. It turns out we've already talked about one of them, that being interference. Although in this lesson, we're going to dive a bit more into looking at the conditions necessary to get constructive and destructive interference. But before we do that, we're going to talk about another important wave characteristic known as diffraction. Learning outcome is to explain qualitatively the conditions for constructive and destructive interference of waves. Let's start off with a new fundamental wave property, that being diffraction. Diffraction is the apparent bending or spreading of waves when they pass around corners, obstacles, or through tiny openings. So one example of this is, again, we could pretend that we're looking at like this from the perspective of like a bird's eye view. So we have like a wavefront. Again, a wavefront from this perspective just means the crest of the wave, and it's moving downward. Now, when it approaches this corner right here, so this would be like a sharp corner, what ends up happening is the wavefront starts to spread, or it starts to bend around the actual corner. And that observation where it does start to bend or spread is what we call diffraction. To explain diffraction, we need to make use of something called Huygens principle. And this is really, really, really complicated. Okay, Huygens principle states that every point on a wavefront may be considered to behave as a point source for new spherical waves generated in the direction of the wave's motion. Okay, we need to break this statement down because there's a lot going on in it, and again, it's quite tough to explain how this principle does work. Okay, so here's how I'm going to do it. So let's look at this diagram and our wavefronts. Now, what this tells me is if we look at a wavefront, we can draw a bunch of little dots we're going to call point sources. So I'll just draw a few of them. So I'll do like one here, one there, one here, and we'll do one right there. So these four red dots are what I'm referring to as a point source. What Huygens principle tells me is that each one of these point sources on a wavefront can behave as the source of a spherical or a circular wave. So think of it like this. If you dropped a pebble into the water at the location of the point source, I would expect a nice circular ripple. So for example, in this case, around this guy, I would get a ripple that might look like something like that. Okay. And around this point source, if you drop a little pebble into the water, same thing. I might get a spherical or a circular wave. Drop a pebble into this point, again. Spherical, circular wave. Drop another pebble into the water. Spherical, circular wave. Now, I drew 4 point sources. You could draw like many more of them if you wanted to, but 4 is going to be enough to illustrate the point here. Now, we need to make use of this to predict what's the next wavefront going to look like. So the first wavefront is a horizontal line. How can we make use of Huygens principle to predict that the next wavefront's also going to be horizontal? If I look at the shape right here, I might think that the next wavefront would just follow the bottom contour of like these little dashed lines. And by bottom contour, I just mean I'm going to trace the bottom parts of these circles. So if I trace the bottom parts of these circles, what I would have is I trace the bottom contour. Maybe I would expect the next wavefront to look like this. Now, obviously it doesn't because the next wavefront is a nice horizontal line. So how do we get a horizontal line? Well, let's look at how these different point sources and these spherical waves are interfering. If you look at these diagrams, there's a small little area where they're overlapping, and I'll shade the little area in. So there's a little overlap area here. we can take this overlap area and we can use it to kind of fill in the gap here. So I can just translate that shaded purple area into this shaded purple area right there. Take this overlapping area, and then I can fill it in down here. Just translate it over. And then I'll do it for the last one. So these guys are overlapping. And then I can just use it to fill in this gap. Okay, so what is that going to do? Well, now that I've filled in the gap, I can actually get a nice horizontal wavefront. Now, this is going to keep happening, so business will be as usual until you get to the sharp edge, and that's where things are going to change a little bit. So let's look what happens if I actually did Huygens principle once I got to the sharp edge. Let's draw the 4-point sources again. So we'll do one here, one there. We'll do one here. We'll do one there. And Huygens principle tells me that each one of these point sources I can pretend is like the source of a circular or spherical wave. Okay, so let's draw what this would look like. So let's draw these circular wave sources, or circular waves from the point sources. Draw the circular waves from the point sources. Okay, and then let's look at what's going to happen here. Okay, so once again, I'm going to trace the bottom contour. So the bottom contour would look like this here. Okay, now let's look at the overlapping areas. So this overlaps. So that's going to fill this gap in. This overlaps. That's going to fill in that gap. This overlaps, and that's going to fill in this little gap here. So most of the wavefront is still going to be a horizontal line, okay, kind of like this here. What I want to focus on, though, is look at the very edge here. Now, unlike in the top little wavefront, there was a wall here, so there's no area for this little part of the contour to spread out. It would just hit the wall and reflect. But now that you've gone around the sharp edge and there's some room for it to spread, this little curved segment right here is actually just going to propagate outward. So it just keeps propagating out, out, and then outward. So you get the bending of the wave around the corner. Similar, I'm not going to go through the Huygens principle for this, but if you had like a wavefront that's approaching a little tiny hole or a slit through here, in this case, like business as usual, you get the horizontal wavefronts until you hit the slit. So again, the key thing is like everything will just be perfectly normal until you hit a corner, an obstacle, or some kind of small opening. And then once you hit that small opening, there's going to be some bending or spreading of the wave. So in this case, when it actually hits the small opening, it starts to radiate outward. Well, this time it's a full arc, well, I shouldn't say a full arc, but it's like a semicircle as opposed to being a quarter arc in this situation. Probably don't need to know that much about Huygens principle, especially at the physics 20 level. I mean, the important thing is we just understand that like when waves do pass through like around a sharp corner or through a tiny opening, there is some spreading of the wave, and that's a property that's referred to as diffraction. Whether or not we need to actually implement Huygens principles is probably not something got to worry about. Go to our other wave property, interference. Although I do want to mention one thing. So again, I did say that diffraction and interference are specific only to waves. So what this means is particles can't do this. So if you have like a tiny slit, when you send like a wave through that little tiny slit right there, it starts to spread apart. It's not like if you took a marble and you fired it through the little slit, that it would spread apart into a bunch of little marbles that would like radiate outward. Okay, that does not happen for like normal matter. Okay, for waves it does, hence a fundamental wave property. Okay, interference. Interference is a condition that occurs when two waves meet they superimpose and they temporarily produce either a larger or a smaller amplitude wave. And a lot of it has to do with like how they meet, like in terms of like in phase or out of phase. Okay, so we know there's two different kinds of interference. You have constructive and destructive interference. We're going to talk more about the conditions necessary to produce this. Constructive interference occurs when crests meet crests or troughs meet troughs, which means that the waves are in phase. We know that. Okay, so let me explain this picture. So in this picture, S1 represents the source of some kind of a wave, and S2 represents the source of another wave. And what we're looking at is we're looking at the sources. So these sources are producing waves, and we're interested in what's happening when these waves meet up at point P. Now, if you look at point P here, it looks like my two crests of the wave are meeting, and my two troughs of the wave are meeting. So at point P, since crest meets crest, trough meets trough, then the waves are meeting in phase. When they meet in phase, we produce something called an antinode or a maxima. Now, if you're wondering how to like maybe memorize this, we'll just think of it like, if you have constructive interference occurring, what are you doing to the amplitude? Well, you're maximizing it. So you produce something called a maxima. The other thing you produce is, and this is the terminology we're going to use like kind of as we move forward here, is an antinode. And the way I'd memorize this one is I think that antinode and amplification both start with the same letter, that being A. So an antinode is a point of maximum amplification for constructive interference. Okay, now here's where it gets a little bit tricky. So we're going to define a bit more in terms of the condition necessary to get constructive interference. So what I've said is constructive interference occurs when the path difference between the two wavelengths is either 0 or a whole number multiple of wavelengths. Okay, so let's talk about what the path difference actually is. Okay, in this equation, P S1 represents the distance from S1, your source of your wave, to point P. P2 or PS2 represents the distance from source 2 to point P, the point we're interested in, like where interference is occurring. If you take these two lengths, so the distance from P to S2, and subtract P to S1, this difference is what we refer to as the path difference. It's showing how much longer one path is in comparison to another one. Okay, that's the path difference. It turns out if the path difference is either 0 or it's a whole number multiple of wavelengths, then you're going to get constructive interference. Now, I'll just quickly like show you like how the diagram illustrates this, and then I'll explain to you why this is true. Okay, so let's count the number of wavelengths from S1 to P. So how many wavelengths would be that you could fit into PS1? Okay, so we're starting here, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so if we wrote this in the equation, PS1 would be 12 wavelengths fit into the distance from P to S1. Well, how about P to S2? What could fit in there? Okay, so let's count the number of wavelengths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so this would be the absolute value of 12 wavelengths minus 13 wavelengths. The reason we put absolute value around here is because we don't want a negative path difference. So 12 minus 13 wavelengths would be negative 1 wavelengths, but this absolute value would just be 1 wavelength. Okay, so if we find the path difference, and the path difference is either a whole number, multiple of wavelengths, like 1 wavelength, 2 wavelength, 3, or it's 0, that is the condition for constructive interference. Okay, now let me explain to you why this is the case. Okay, so I'm gonna have to just manipulate this slide here to show it. Okay, so on this slide, let's look at these two waves. Okay, so I have two waves, the same wavelength and the same amplitude. And what I'm going to do is I'm going to just take this wave and I'm going to directly put it over top of the other one. Okay, so it's directly on top now. Let's go back to the slide. Now, what I'm going to do is I'm going to take one of those waves and I'm going to move it over by a whole number multiple of wavelengths. So I'm going to take one of them and I'm going to move it over by one wavelength and see what happens. So I'll take one of them and move it by one wavelength. To move it one wavelength of distance, that'd be the distance in going from one crest to another crest. So we'll move it over by one wavelength, okay? And then let's see what happens now. Okay, so I'm going to move, I think it's the red one I'm going to move over, and I'm going to move over by one wavelength and see what this looks like. So if I move it over to the right, move it over to the right, we'll stop it once, move it over by one wavelength. Okay, this would be moving it over by one wavelength. Now, when you move it over by one wavelength, the waves actually perfectly overlap again. If you're wondering why they don't overlap right here, that's because I was attempting to draw the waves with the drawing tablet and I could not draw a perfect wave. But if you do take one wave and you move it over by one wavelength, they still meet in phase. In fact, if you move it over by two wavelengths, the same thing should happen. So if I just keep moving it over, this would now move over by two wavelengths. Again, they're in phase. If there's no path difference between them, they'd just be sitting on top of each other, in which case they're always in phase. So that's why, if the path difference is a whole number multiple of wavelengths or zero, then constructive interference occurs because that would result in the waves still being in phase with each other. Okay, let's look at destructive interference. So destructive interference occurs when the crest of one wave meets the trough of another. So they meet out of phase. It's kind of hard to see it in this illustration, but in this illustration, it's trying to show that the trough of one wave does meet the crest of another one at point P. When this occurs, you produce something that are called nodes or minima. Well, what's happening in destructive interference? In destructive interference, you are minimizing the amplitude. In fact, you might even make it zero, hence the word minima. In terms of like memorizing the term node associated with this, I would think that node and nothing both start with the letter N. Nothing in terms of no amplitude. In order to get destructive interference, you need your path difference between these waves to be, what I would call it is like half a natural number multiple of a wavelength. So it's got to be a value that's either like 0.5 wavelengths, it's got to be 1.5 wavelengths, or it needs to be 2.5 wavelengths, etc. Okay, I'm not going to go through the tedious task of actually like counting the wavelengths here, but I believe you do calculate the wavelengths and you find the path difference, you do just get 1/2 of a wavelength. Okay, so if the path difference is half a natural number of a wavelength, then you do get destructive interference. Now, once again, why is this the case? So why is if it's offset by half a wavelength? Okay, so let's just go to this slide here. Okay, so what I'm going to do is, first of all, let's take the waves and let's put them on top of each other. Let's stack them. Okay, so I have these two waves stacked.
Hello, could you call me when you have a minute?
Okay, and I'm going to take one of those waves and I'm going to move it over by a half wavelength. Now, a half wavelength would just be moving it from a crest to a trough. So that would just be moving it to this position. So that would be 1/2 of a wavelength, lambda divided by 2. Okay, let's see what happens when I do that. Okay, so let's move it over. I'll stop when I get that crest to half a wavelength, and that's about right here. Well, look what happens at this point. I now have the crest of one wave meeting the trough of another one. So if they're off by half of a natural number or half a wavelength, they're now out of phase. And if you went to 1.5 wavelengths, I just keep shifting it over. So this would be one wavelength. 1.5 wavelengths would be at a position that's about here. So once again, the reason that destructive interference occurs when the path difference is half a natural number is because if you moved one of the waves over by half of a natural number, then the two waves would meet out of phase. Okay, one other note here. I said although waves can be reflected and refracted, and we've talked about that. We talked about how when waves hit a surface, they can bounce back, or if they go from one medium into another one, they can be refracted. Those are property of waves. We don't refer to them as being fundamental wave properties. The reason they're not fundamental wave properties is because other objects like particles can do this. So, for example, if you had like a surface and you took a marble and you shot it straight down, it would hit the surface and it would bounce up in accordance with the law of reflection. So it's not a property that's restricted just to a wave. Well, how about refraction? Well, if you took an object and let's say, let's make this water. Let's say this is water here. So if you had an object, maybe like a bullet, and it was like fired like, not that I'm encouraging you to do this, but like if you had like a bullet and you're firing it like straight down at the water, what would happen is when it hits the water, its speed would change. And not only would its speed would change, so would its direction. So if the water wasn't there, it would just keep moving in a straight line. But if it goes into a slower medium, I would expect the direction of motion to be towards a normal line. So this guy would bend a little bit, so its direction would change just a little bit here. Sorry, that was a really awful picture of how the wave rate bends. So yeah, so particles can undergo refraction as well, because when they go from one medium into another one, their speed can change and so can their direction. Does their wavelength change? That's a complicated question. We'll leave that for physics 30. Because does a particle have a wavelength? Again, we'll leave it for later on. Okay, this is an illustration of something that's called I think a wave or ripple tank. And what's going on in the ripple tank is you have like these two stir sticks. These two stir sticks you can think about just from the center right here. It's like dropping a pebble into the water, and a pebble in the water, of course, would just have like the energy radiating outward in a circle. Okay, so that would be like one source, which you could call S1. Over here we have another stir stick, S2, and then once again we just have the wave energy that is going to radiate outward. Now the interesting thing is that when these two waves overlap, they start to form something that we refer to as an interference pattern. Now, if we look at the actual picture, you should see like these spots where like I have kind of like a light spot followed by a dark spot, light spot followed by a dark spot. These light spots, like right here, that would represent a crest. And this dark spot here would represent a trough. These areas where it looks like it's a little bit fuzzy, this would be where the water tank would be at its rest position. So if there was nothing stirring the water, that's what it would look like. It turns out the rest position is what we refer to as a node, because what happens at a node? At a node, there's no amplification. If you have no amplification, you'd be sitting at the equilibrium position or the rest position. So we have these nodes here. Now, directly in between the nodes, we would have our antinodes. So our antinodes are either an area where we have like a maximum crest or a maximum trough. And it just keeps alternating between trough to crest, trough to crest, trough to crest. We call this an interference pattern because what's happening is we're constantly alternating between a node and antinode, a node and antinode, etc. And right here we'll be back to like another antinode, a node, back to an antinode, back to a node, etc. This will be more of a big deal when we talk about light in physics 30, but I just wanted to point out that when the when the wave does diffract and overlap and interfere, you do get this alternating pattern of nodes and antinodes. Okay, quick example. It says points S1 and S2 are sources of identical water waves. PS1 is 80 centimeters. Well, let's label that. So 80 centimeters. And then PS2 is 90 centimeters. And it says identify if we're going to get constructive or destructive interference at point P if the sources produce the following wavelengths. Okay, so this is my wavelength. The question we're really looking for here is we're going to figure out the path difference to start off with. So let's calculate that. So my path difference would be PS1 minus PS2, which would be equal to PS1 is 80 centimeters. Subtract 90 centimeters. And if you take the absolute value of that, 80 minus 90 would be negative 10. Absolute value would just be 10 centimeters. Okay, that's my path difference. Now, to identify whether it's constructive or destructive interference, it's just a matter of, can you fit a whole number multiple of wavelengths into the path difference? If you can, it's constructive interference. If you can fit only a half multiple of wavelengths in there, it's going to be destructive. So we can determine this by just taking the path difference and dividing by the wavelength. So let's call this, let's abbreviate it as PD, okay, path difference. So I'm going to take the path difference and I'm going to divide by the wavelength. So what this is going to do is it's going to tell me how many wavelengths you can fit into the path difference. Okay, so this would be 10 centimeters divided by a wavelength of 5 centimeters, and that would be equal to 2. Okay, that should make sense. If your path difference is 10 centimeters and your wavelength is 5, I can fit 2 wavelengths into that. Now, if you can fit a whole number multiple of wavelengths in there, so I can say, since we have a whole number of wavelengths fit into the path difference. Therefore, constructive interference. Okay, B. Okay, we've got a much bigger wavelength now. So, I mean, the path difference is 10 centimeters. The wavelength's 20. We can't even fit one wavelength in here. But let's see what happens if we divide. So we'll take the path difference and divide by the wavelength. So the path difference would be 10 centimeters. Divide by the wavelength to 20 centimeters. And that would give us 0.5. So that should make sense. The path difference is 10 centimeters and our wavelength is 20 centimeters. We can only fit 1/2 of a wave into the path difference. Okay, so I'm going to say since you have half of a natural number of wavelengths fit into the path difference. Therefore, destructive interference. Okay, that's it for this lesson. You can complete the assignment. It's called Diffraction and Interference. I wouldn't stress too much. Like I think one of the first questions involves you just trying to sketch what the wavefront patterns looks like around certain obstacles. I mean, just do your best to sketch it, show the spreading. You don't have to do it technically as accurate as it should be using Huygens principle. And then I think the back page has some questions dealing with the path difference. And then in the next lesson, we're going to start to talk about mechanical resonance. And that's going to lead us pretty much until the end of the unit. And I'll talk to you then.